Good morning, students. Under the discrete mathematical structure, module 2 is based on the properties of the integers and fundamental principles of counting. So under the properties of integers, you will be learning regarding the mathematical induction. So this is in one chapter. And under the fundamental principle of counting, which is the next chapter, you will be learning regarding the rule of sum and product, permutations, combinations, binomial theorem, as well as combination with repetition. So in this session, let us learn regarding the mathematical induction. So I've just mentioned over here mathematical induction 1 and mathematical induction 2 videos. So that is nothing but continuation of one and then continuation with the second video. So let us see the definition of mathematical induction. So mathematical induction states that it is actually based, mathematical induction is actually based on, mathematical induction is based on the well-ordered principle. Okay, is based on, mathematical induction is based on the well-ordered principle. So what do you mean by well-ordered principle? Well-ordered principle states that it's based on well-ordered principle. So it is nothing but principle which has the set of all positive integer and it should be well ordered. So it includes z plus denotes nothing but set of all positive integers, set of all positive integers, set of all positive integers. These set of integers should be well ordered. So mathematical induction is again based on the principle of induction principle itself, but again this induction principle can be proved by another principle called well-ordered principle. So well-ordered principle states that every non-empty subset of z plus, every non-empty subset of z plus contains a smallest element. It must contain a least element. So alternative way of stating this principle is that set of all positive integers is well ordered. So that is what is the meaning of well ordered principle. So now let us see the definition over here. Over here we have told that suppose we wish to prove that certain statement s of n, for example, let us take an example like s of n actually contains a statement like 1 plus 2 plus 3 plus so on till n, okay, is equal to half of n into n plus 1. Okay, so this is the statement. This is a statement. Here s of n denotes a statement that involves a positive integer n. That this is nothing but a statement which involves a positive integer n. Suppose let us consider this particular example. Now what do you mean by mathematical induction is it actually has two steps. One is basic step and second one is the induction step. So now over here you need to prove for one step, basic step is for when n equal to 1, okay, and this is the basic step. That means if it is when n is equal to 1, if this statement is also equal to 1 itself, you give, for example, try over here, s of 1 you do, s of 1 if you give, you know, half into 1 into 1 plus 1. So what you got the answer as? This is 2 by 2, this 2 and this will get cancelled. So answer is 1. So here also left hand side you add value 1 and here also right hand side you got 1. So basic step is verify that statement s of 1 is true. That is verify that s of n is true for n equal to 1. That means when you take n equal to 1, the value also s of n, whatever the value is there in the right hand side, you should get it as 1. So this is the basic step you have to prove while doing the mathematical induction. Okay, induction step is you assume that the s of k is true. That means instead of n, right, we are replacing with k here. We assume that s of k is true. By assuming s of k is true, we try to solve that. We try to solve s of k plus 1. If we get this as true, then your entire this problem, that means s of n, whatever the statement, is equal to this by the principle of mathematical induction. So suppose we wish to prove that certain statement s of n is true for all integers n greater than or equal to 1. The method of proving such a statement on the basis of the induction principle is called the mathematical induction. So it includes basically basic step and induction step. So basic step is nothing but verify that the statement s of n is true for n equal to 1. Here you are replacing with n equal to 1. Then you are assuming that it is true for s of k. It is true for s of k, where k is an integer that is greater than or equal to 1. And based on assumption of s of k is true, you're assuming s of k is true, try to prove for s of k plus 1 is true. If you get this as true, then whatever this statement we have declared, that prove that by mathematical induction for all positive integer n greater than or equal to this is equal to this, then for all positive integers, that is n greater than or equal to 2 or z plus, this statement is true. This is what is the concept of mathematical induction. So let us go and solve the problem. So example 1, prove by mathematical induction that for all positive integers n greater than or equal to 1, 1 plus 2 plus 3 plus 4 plus so on up till n, half into n plus 1. So this we have to prove. So again we have to mention the basic step and induction step, and we have to try to prove. So let us solve in a new page. So the first problem is based, what we are supposed to solve is nothing but 1 plus 2 plus 3 plus 4 plus so on plus n is equal to half into n plus 1. Okay, so this is a statement. What is a basic step? For this we have to solve the basic step. So this is a question. They have told question is nothing but prove by mathematical induction for all positive integers n greater than or equal to 1, this is equal to this. Okay, this is equal to this. So what we are supposed to prove here? Here we are supposed to prove that, just right over here. Here we are supposed to prove that. Here we are supposed to prove that s of n, that is s of n stands for what actually? Statement that involves a positive integer n. Statement that involves a positive integer n. So s of n 1 plus 2 plus 3 plus 4 plus so on plus n is equal to half into n plus 1 for all integers n greater than or equal to 1. For all integers n greater than or equal to 1. So what is the first step we have to do while solving? Here write down the statement. We need to prove this particular statement. We need to prove this particular statement. So the basic step we have to write. Solution is from here. Basic step. What is a basic step? If you see the previous slide, basic step, you know what you are supposed to do. Verify that the statement s of 1 is true. Basic step is s of 1 is true. Induction step is assume that s of k is true. Basic step, we need to verify that s of 1 is true. If you verify this is true, then only you can go to the induction step. Okay, so here nothing but n value you need to take it as 1, and you need to get the answer as 1. So let us go and solve over here. Basic step, we note that basic step is nothing but we note that s of 1 is a statement. S of 1 is the statement. So you see here, instead of n I took 1. S of 1 is the statement. So how will you prove this particular statement? So here s of 1 is the statement. So just first value need to take 1, because only for one value select 1 equal to half into n value is 1 now, 1 plus 1. So what is this? Half into 2. So this and this get cancelled and you got 1. So left hand side is equal to right hand side, which is clearly true. So just write over there which is clearly true. The statement s of n is verified. S of 1 is verified for n equal to 1. So this is regarding the basic step. Now you came to know that we proved that s of 1 is true. That means what he told actually in the induction principle, that verify that s of 1 is true. So you came to know that when you took s of 1, nothing but the first value. So I cannot take these values. It's only for the first value. Instead of not, you cannot take 1 plus 2 plus 3 plus 4 till dot. So it's only one value. So I took 1, that is equal to half into 1 plus 1. So you got to know 1 is equal to 1, which is true, and we verified that that is true for n equal to 1. Now what is our induction principle? Our induction principle is nothing but induction principle. Induction principle, we assume that statement S of n, we assume that S of n is true for n equal to k, where k is an integer greater than or equal to 1. Okay, where k is an integer greater than or equal to 1. So same thing, whatever this here, instead of n we took k, so that should be greater than or equal to 1. Now let us solve for S of k. So we assume that S of k, instead of n we wrote k, so this will be nothing but 1 plus 2 plus 3 plus 4 plus so on plus k, then that is equal to half into k plus 1, half into k plus 1. Using this, we have assumed, using this try to prove for k plus 1. If you get k plus 1 also true, then we came to know that this entire statement is true by mathematical principle, mathematical induction principle. Using this, we find that instead of k you replace with k plus 1. How it will be? Next term. Using this we find that you should prove that it is true for k plus 1. So this is in terms of k, right? So instead of k we again need to add k plus 1 both the sides. So we'll just add for this particular statement. So it will be nothing but 1, this is 1 plus 2 plus 3 plus 4 plus so on plus k. This is kth term. In case if I wanted k plus term, so what it will be actually? Plus k plus 1. Okay, this we wrote for k, right? So this is for k. When it comes to the k plus term means what? Plus next term, right? So plus k plus 1, and here also it will be half, both the side you have to add k, right? K plus 1, right? So you added k plus 1 this side, so even here you have to add. So here also it will be k plus 1. So you came to know that here it is k. You try to prove for k plus 1. So here I put k plus k plus 1. Here I got half into k plus 1 plus k plus 1 plus k plus 1. So the continuation I will do it over here. I'll solve this right hand side. So what will get the right hand side? This k plus 1 and this k plus 1 is common. So can I take k plus 1 out? So I took k plus 1 out, and here it will be half k plus 1. Okay, so k plus 1 is out. This, if I take LCM, what it will be? K plus 2 over here, 2 into 1 divided by 2. So it is nothing but half into k plus 1 into k plus 2. So this is what we got actually the result. So just try to compare with k, replacing with k. So this is for k plus 1. So just try whether it is true for k plus 1. See, S of k we got this way. We assume this is true. So if it is k, you got it half k plus 1. If it was k plus 1, how will this equation be? I'll just write it here. Half, instead of k it should be k plus 1. So it will be k plus 1. This k will be again k plus 1 and plus this one. So it is nothing but half into k plus 1 to k plus 2. So this is the required result. I need to get it when it is k plus 1 when I'm going to add. Instead this was for k. When I take it as whether it is true for k plus 1, I will actually replace k with k plus 1. So half into k plus 1, k plus 1 plus 1. So it will be, this is what I'm supposed to write. So same way I just solve this left hand side. See, 1 plus 2 plus 3 4 plus k, this I assume to be true. Based on this I try to solve for k plus 1. So you know k plus 1 is the next term of k. So I need to add k plus 1. So for this entire thing is equal to this particular equation. So I just replace this equation with this equation. So that's what I did, half into k plus this k plus 1 I did. So when I solved, I got this particular result. Then you verify background, go back and verify whether when you put k plus 1, what you will get, half into k plus 1 plus k plus 2. So this is the required result and these both are same. Okay, hence this statement is true. Hence the statement is true. Hence this statement is true for S of k plus 1. Hence this statement is true for S of k plus 1. Thus on the basis of assumption that S of n is true for n is equal to k, thus on the basis of assumption that S of n is true for n equal to k greater than or equal to 1, the truthness of this is been established. Okay, so S of n is true for n equal to k greater than 1, that is, this truthness is been established. So here you just need to write, hence the statement is true for S of k is equal to 1, hence S of n is true for n equal to k greater than equal to 1. S of n is nothing but this entire statement is true for n greater than or equal to n is equal to k greater than or equal to 1. So we have first have taken n that is equal to k greater than or equal to 1. So this is based on the example problem of mathematical induction. Okay, so you need to, basic step is nothing but you have to take for S of 1. Induction step is you are assuming that S of k is true. Based on this assumption, you are trying to prove that it is true for k plus 1. So what I came to know that this left hand side is equal to right hand side I have assumed. So I have just added plus k plus 1. So you know that this entire term is equal to this. So that's what I have written over here. Plus k plus 1 I added. And then try to solve. I got this particular equation. So I compared this with this. When you do k with k plus 1 and this k plus 1, this k will be k plus 1 and this k also will be k plus 1. So it will be half into k plus 1, k plus 2. So that is what is this particular equation. So this is regarding the example 1. So next example 2 is based on prove that for each n that belongs to z plus is nothing but set of all positive integers, 1 square plus 2 square plus 3 square plus so on up till k square is equal to this particular term. So let us try to solve this in a new page. So let us take directly the S of n. I'll write directly. S of n is nothing but we have the S of n as 1 square plus 2 square plus 3 square plus so on plus n square is equal to 1 by 6 n into n plus 1 into 2n plus 1. Okay, so this is S of 1. So what we have to prove is this is equal to this when n equal to 1 and then when n equal to k, we are assuming, by assumption we are proving that it is true for k plus 1. Then we know that if we prove for k plus 1, then this is equal to this. So let us first we'll take the basic step. So what is the basic step? So basic step, we know that we verify for S of 1. We verify for S of 1. So just S of 1, right? So you have to take first term. So what is the first term? 1 square. And here in the right hand side, it is 1 by 6 into n. What is n value now? S of n value is 1 into 1 plus 1 into 2 into 1 plus 1. 2 into 1 plus 1. So you know that this is 1 by 6 into this will be 2 and this will be again 2 plus 3. So it's 3. So again you know that 3 2s are 6. So this and this will get cancelled. So again the value is 1. So from this we know that LHS is equal to RHS. So which is clearly true. From this we know that S of 1 is true. S of 1 is true. Now what will be the induction step? Induction step, we assume that S of n is true for, we assume that S of n is true for n equal to k for what? Positive integers, right? So for k greater than or equal to 1, so the statement is s of k 1 square plus 2 square plus 3 square plus so on plus k square, that is equal to 1 by 6 into k to k plus 1 into, instead of n it will be 2k plus 1. Okay, so 2k plus 1. So this is 1 square plus 2 square. This is what we are going to be, we are going to assume that this statement is true. This statement is true. What we have to do that, based on this statement is true, we need to prove that it is true for k plus 1. So what I need to do, k plus 1 is the next term. So I'll just take this LHS, okay, this LHS. So what it will be actually 1 square plus 2. We are trying to prove for k plus 1, okay, we are trying to prove for k plus 1, so it will be 1 square plus 2 square plus 3 square plus so on plus k square. After that, next term, what will be the next term? This is k square, so next term is k plus 1 whole square. So what is that? Adding k plus 1, adding k plus 1, okay, adding k plus 1 whole square, adding k plus 1 whole square. So I just added for the left, I added to the left hand side, so it will be, this is actually what, you know that this entire thing is equal to this part, so just write as it is, 1 by 6, that is equal to 1 by 6 k plus 1 equal to 2k plus 1 plus k plus 1 whole square plus k plus 1 whole square. One way you can take only this LHS and that k square is there. Next term you're going to add a whole square, you can do that, or else you can add next term here k plus 1 whole square, and here also plus k plus 1 whole square, both are same. If you add to this term, you know that this entire term is equal to this term plus k plus 1 whole square is also fine. You can write adding k plus 1 whole square both sides also, no issue, one and the same, both sides, okay. Over here, then try to solve this, try to take C. Now you know that when it is k, it is this, okay, when it is k, you got this. So I'll just write what final answer you should get, I'll just write over here. When it is k, it's this. Finally, you should get 1 by 6. Instead of k, it should be for k plus 1, right? So just replace k with k plus 1, final answer. So k plus 1 plus 1, and then 2 into k plus 1 plus 1. So this is nothing but 1 by 6 into k plus 1, k plus 2, 2k plus 2. That will be nothing but 2k, 2 into k plus 2 plus 1. So it is nothing but 2k plus 3. So when it is k plus 1 whole square, you should get this. This should just keep it in mind. No need to solve this. This is what is you're supposed to get. In pencil, you can just solve. This is what you need supposed to get. So try to solve over here. What is common over here? This. Try to solve over here. What is common in this particular section? K plus 1 whole square is there. So what can I take the common term over here? I can take k plus 1. I can take k plus 1 as the common term. So what will be within the bracket? It will be 1 by 6 k into 2k plus 1 plus k plus 1. 1k plus 1 is out, right? So plus this term. So it is nothing but k plus 1. So this will be, you know, this is entirely for this. So this will be k into 2k plus 1, k into 2k plus 1, okay, and plus 6 into k plus 1 divided by 6. Now I try to multiply this. What you will get it as? So it is nothing but k plus 1, as it is k plus 1. Here you will get it as 2k square plus k plus 6k plus 1. 2k square plus k, 2k square plus k plus 6k plus 1 divided by 6. So I'll solve the continuation over here. Continuation is over here. So over here I'll get, try to this. What is this? That is in the form of 2k square, sorry, 1 second, it is in the form of k plus 1 out, then you have 2k square 2k square, k plus 6k will be 7k plus 1. Sorry, here it should be plus 6, not 1. It should be 6k plus 6, right? So it is plus 6. So how can I solve? You know how to solve this. So when you solve this k plus 1, so this will be in the form of 2k square plus 7k plus 6. So that is again 6 2s are 12. So this and this when you multiply you will get 12. So it is nothing but 4 3s are 12. So I can split this into 4 and 3. So it will be nothing but 2k square plus 4k plus 3k plus 6. Okay, sorry, here I missed entire thing, division by 6 here, division by 6. So this is by 6. So what it will be again, k plus 1. So this is nothing but you can take common. So if I take, let it be this. If I take 2k common, it will be nothing but, if I take 2k common, it will be k plus 2, and if I take 3 common also, it will be k plus 2 by 6. So here it will be nothing but k plus 1 into k plus 2 into 2k plus 3 divided by 6. So that 6 I can take it as 1 by 6. So just check k plus 1, k plus 2, 2k plus 3. So that is what I wanted to get. So you came to know this is true for k plus 1. So this statement is precisely this statement is true for s of k plus 1. So you can write therefore this is true for s of k plus 1. Hence s of 1 is true by mathematical induction. So this completes the proof of required by mathematical induction. So this is regarding the second problem. Now let us go to the third one. Prove by mathematical induction that this is equivalent to this. So let us solve in a new page. Again they told mathematical induction. So the question is 1 plus 3 square plus 2n square. Okay, so we'll write here that is 1 square. I'll write this as s of n. Okay, so directly s of n, 1 square plus 3 square plus 5 square plus so on plus 2n minus 1 whole square is equal to 1 by 3 into n, 2n minus 1 and 2n plus 1. Okay, 1 square plus 3 square plus 5 square plus so on, 2n minus 1 whole square equal to 1 by 3 into n, 2n minus 1 into 2n plus 1 for all integers n greater than or equal to 1. So let us directly I'll write the basic step. So you know basic step is what you're going to prove for s of 1. So you're going to prove for s of 1. So s of 1 means first term, that is 1 square directly is equal to 1 by 3 into 1, 2 into 1 minus 1, 2 into 1 plus 1. So you know that this will be 1 by 3 itself. 2 minus 1 is 1. 2 into 1 plus 1 is 3. So this 3 and this 3 get cancels and this is 1. So therefore s of 1 is true. We verified that s of 1 is true. Now we have to do the induction principle. Induction step. So what is induction step? So what is induction step? We assume that s of n is true for, always write that, assume that, this statement is important, okay, assume that s of n is true for n equal to k, that is greater than or equal to 1. Then 1 square plus 2, then 1 square plus 3 square plus 5 square plus so on plus 2k minus 1 whole square is equal to 1 by 3 into k, 2k minus 1, 2k plus 1. Okay, so this is equal to 1 by 3k. This is what we are going to assume. Okay, 1 by 3 into k is into 2k minus 1 into 2k plus 1. Now based on this assumption we have to prove that it is true for k plus 1. So what will happen over here? Let us take left hand side itself. So 1 square. This is our assumption. We assume that this is true. By this we have to prove that it is true for k plus 1. So 1 square plus 3 square plus 5 square, so on. So this is directly your what? K itself. So it will be 2k minus 1 whole square. 2k minus 1 whole square. For this, k should be replaced now by k plus 1. So what it will be? Since it is this k, so it will be 2 into k plus 1, k2 in minus 1 whole square. So you know that this term is nothing but 2k plus 2 and minus 1. So it will be nothing but 2k plus 1 whole square. So this is our left hand side. So you know that this entire section we have as this. So let us put over here. This is LHS. This is LHS. So this, you know, this section is equal to this particular section. So just write over there 1 by 3k 2k minus 1 into 2k plus 1. So that is half section, and plus this section. What is this section? I'll directly solve within this. It is nothing but, you know, that 2k plus 2 minus 1. So 2k plus 2 minus 1 is nothing but 2k plus 1 whole square. So what can I take the common term over here? I'll write over here itself 1 minute. So what can I take the common term? So it is nothing but 2k plus 1. So take 2k plus 1 as a common term. So within the bracket you have 1 by 3 into k into 2k minus 1. 2k, this is k, okay. 2k minus 1. 2k minus 1 plus here 1 2k plus 1. Okay, so this is our section. So what you can do is again take LCM. So here 2k plus 1 will be out. When you take LCM again, k into 2k minus 1 plus 3. I'll directly multiply this, okay. 3 into 2k plus 1 divided by 3. So you can take this 3 out here. Again it is 1 by 3 now. 2k plus 1 over here. Now try to multiply. What will be this? This will be 2k square minus k plus 3 into 2. It will be 6k plus 3. Okay. So this is what you're supposed to, you'll get 2k square minus k plus 6k plus 3. So here let us see, here you have just for k. Now if you assume what you have to get the output actually for k plus 1, it is nothing but 1 by 3 into k plus 1. Instead of k you should get k plus 1, and then 2k, here it is 2k 2 into k plus 1, right? So it will be 2 into k plus 1 minus 1. So it is nothing, we'll see in the next step. Then again you have 2 into k plus 1 plus 1. Okay, 2 into k. So I'm just solving this. What we are supposed to get, that I'm just checking. So it is k plus 1, and this will be like 2k plus 2 minus 1. So it is plus 1. 2k plus 2 minus 1 plus. Here it is 2k plus 3. So this is what I have to get over here. So you can see one part I already got, 2k plus 1 I already got, 1 by 3, this is there, this is there, and this is there. I need to get these two terms. So let us see how can I solve further. We'll see in this particular section. So here continuation over here, okay. So 2 that is equal to 1 by 3 into 2k plus 1, 1 by 3 into 2k plus 1, and this can be solved as 2k square minus plus 5k plus 3. So you know that it is again in the form of 2k square plus 5k plus 3. So you know that 3 2s is 6. Correct, 3 2s is 6. 3 2s is 6. So how can I get it again in this term? So it will be nothing but 1 by 3, factorize it, 2k plus 1, factorize this particular term. So it will be nothing but 2k square plus 3k plus 2k plus 3. This is plus 3. So this is plus 3. So it will be nothing but 1 by 3 into 2k plus 1. So it will be Here 2k square will take this cell, right this side, you write this side. Okay, so it will be 2k out, so it will be k plus 1, and here these two terms you combine. I took 3 out, so it will be k plus 1. So it is nothing but 1 by 3 into 2k plus 1 into k plus 1 into 2k plus 3. You can rearrange this if you want in this particular order. So it will be 1 by 3 into k plus 1 into 2k plus 1 into 2k plus 3. So this is what is the required result. So therefore it is true for S of k plus 1. Hence S of n is true by mathematical induction. Therefore it is S of k plus 1 is true, and finally you should write hence this is true by mathematical induction. So this is how we are going to solve the third example. Next, let us go to the fourth one. The fourth one is, if n is any positive integer, prove that this is equal to this, this is equal to this. So let us see the example in the new page. Let us solve this particular problem in the new page. So question is S of n, will write directly S of n denote the given statement. Okay, S of n denote the given statement. So that is nothing but 1 into 2 plus 2 into 3 plus 3 into 4 plus so on plus n into n plus 1, that is equal to 1 by 3 into n plus 1 into n plus 2. Okay, n into n plus 1 into n plus 2. So what is this? You have to prove this using by the mathematical induction. So let us first, we are basic step is what? Basic step is nothing but for S of 1. Basic step is for S of 1. So this element you have to take. So what is that? 1 into 2. 1 into 2, that is the first element. For first one, 1 into 2, you cannot take further elements. 1 into 2 is equal to 1 by 3 into 1 into 1 plus 1 into 1 plus 2. So that is actually equal to 1 by 3 into 1 into 2 into 3. So this 3 and this 3 got cancelled. So left hand side was 2 and here also you got 2. So that is equal to 2. So both are, S of 1 is true because both the sides you got, when S of 1 is true, both the side LHS and RHS is equal. So S of 1 is clearly true. S of 1 is clearly true. Now let us see the induction step. Induction step. So what is happening in the induction step? We assume that it is true for, we assume that S of n is true for, S of n is true for n equal to k, where k is greater than or equal to 1. K is greater than or equal to 1. Then (1) (2), (2) (3), so this so on, plus k into k plus 1 is equal to 1 by 3 into k plus 1 into k plus 2. So this is what we are going to assume to be true. By this we are telling that it is true for k plus 1. So what will be? Let us take LHS itself. So what will be added over here? This is as existing itself. Next we have to add k plus 1. So k will be replaced with k plus 1 and here it will be replaced with k plus 2. Either you can add to the both the sides. I'll just take LHS and I'll try to solve. So LHS is equal to what? Left hand side this. So that is nothing but 1.1 into 2 plus 2 into 3 plus 3 into 4 plus so on. I'm trying for k plus 1. Okay, after I'll write over the way. Plus here k into k plus 1 as it is I wrote. Then adding k, here you write adding k plus 1. Adding k plus 1 into this will be k plus 2, right? So adding k, replace with k, what it will be? K plus 1 into k plus 2. So what you have added you should write over here. Okay, I'll write here itself k plus 1, k plus 2. Adding k plus 1. Adding k plus 1 plus k into k plus 2, both the sides you have to write, okay, both the sides, because it is same. If you put for LHS over here, next term, then this term also will be plus k plus this particular term. So what it will be now, this is actually equal to 1 by 3, this is as it is, right? So this term 1 by 3 into k plus 1 into k plus 2 plus these two terms you have added. So it will be k plus 1 into k plus 2. Now what is common? K plus 1 and k plus 2 is common. So what will be within the bracket? 1 by 3k plus 1. 1 by 3k plus 1, because this I took both common, so 1 will be remaining. So what will be the next step? It will be nothing but k plus 1, k plus 1, k plus 2. If you take LCM, it will be k plus 3 divided, this 3 will go over here, divided by 3. So that 3, if I take, it will be 1 by 3 k plus 1 k plus 2 into k plus 3. So this is how we are going to solve regarding the equation. So you just compare over here, what if you put k plus 1, how you will get? So it will be k plus 1, this will be k plus 2, and this will be k plus 3. So that we got as it is. So it is true for, it is precisely true, or it is true for s of k plus 1, s of k plus 1. Therefore by mathematical induction, s of 1 n is true for n greater than or equal to 1. So this is how we are going to solve. So here main induction step, basic step is clear. For the first term you solved 1 into 2 you got, and both the side 2 equal to 2, it is true. Then you assume that it is true for s of k. So you wrote this, and then you know that when you assume for k, you need to prove it for k plus 1. You're going to prove it for k plus 1. So this k will be k plus 1 and this will be k plus 1. So k plus 1 will be k plus 2. So these two terms you can add for both the side, adding k plus 1 and k plus 2, both sides you can mention, because however the meaning is same. For this only you are adding these two terms, right? So both the sides you have to add. Actually it is both the sides. Then you will try to solve. So it will be in the form of k plus 1 for this itself. For this, if you add k plus 1, here if again you put k plus 1, it will be k plus 2 actually. Here it will be k plus 3. So we got the required result for s of k plus 1. So by mathematical induction, it is true for n greater than or equal to 1. So this is regarding the example 4. Example 5 is based on proof by mathematical induction that n factorial is greater than or equal to 2 power n minus 1 for all integers n greater than or equal to 1. So let us solve this in next page. So the question is, let us take s of n itself. So the s of n we have as s of n is nothing but n factorial, so that is greater than or equal to 2 to the power n minus 1, 2 to the power n minus 1. True for all integers n greater than or equal to 1. So what is a basic step? Basic step is nothing but, basic step we have, basic step is for n equal to 1. For n equal to 1 we are going to verify. So what is that? For n equal to 1, that is s of nothing but s of 1 is true. Verify s of 1 is true. So over here, that is nothing but 1 factorial you are going to check is greater than or equal to 2 to the power 1 minus 1. So that is nothing but 1 factorial is 1 itself, that is greater than or equal to 2 to the power what? 0. So that is nothing but it is equal to 1 greater than or equal to 1 itself. So we got 2 to the power 0 is none, which is obviously true, which is obviously so. So s of 1 is true. So this is regarding the basic step. Next is regarding the induction principle. Okay, induction step. So over here we assume that s of n is true. S of n is true for n equal to k, where k is greater than or equal to 1, that is we assume that k factorial is greater than or equal to 2 to the power k minus 1. 2 to the power k minus 1. So this is our assumption. From this we need to prove that k plus 1 factorial, what we are supposed to prove that actually, from this we are supposed to prove that, I'll just write over here, okay, what you're supposed to prove is nothing but it is also true for k plus 1 factorial, that is greater than or equal to 2 to the power k plus 1 minus 1. So that is nothing but greater than or equal to 2 to the power k. So we should get finally the result as k plus 1 factorial greater than or equal to 2 to the power k. So here we have this as k. So how can we write this particular term? So let us take in this way. I'll just interchange the term 2 power k minus 1. So this is less than or equal to k factorial. So just interchange this particular term. What I did is I just took k this side and this side. So the operator gets changed. Greater than is actually k factorial. So it's pointing over here. Now you know that this is nothing but 2 to the power k divided by 2 to the power 1. 2 to the power 1. So you know when it goes to the numerator it will be 2 to the power k minus 1. That is nothing but greater than or equal to k factorial. So can I write 2 to the power k? This 2 I'll take it over here. So that will be nothing but 2k factorial. 2k factorial. So I'll repeat. This was k factorial, our assumption, greater than or equal to 2 to the power k minus 1. I just interchanged the term. I wrote 2 to the power k minus 1 less than or equal to k factorial. Meaning is same. These both statements are same. Then I just took 2 to the power k divided by 2 to the power 1. Meaning is same. 2 power k minus 1. This 2 I multiplied with this. So I got this particular step. So you see over here, this result I got it. This result I got it over here. Okay, this result I got it over here when it is for the k plus 1. This side I want k plus 1 factorial, but you have k plus k factorial. But this 2 is there. I should replace 2 with what? So that I should get k plus 1 factorial. So what I'll do is k plus 1, I'll replace 2 with k plus 1. K I'll write as it is as k factorial. So that is nothing but what? K plus 1 into k factorial is k plus 1 factorial. That you know the meaning of k plus 1 into k factorial is next. Now for example, if you had 3 into 2 into factorial, so meaning is what? What is 3 into 2 into 2 factorial is 2 into 1. So that meaning is nothing but 3 factorial it says. So same way over here, k plus 1 into k factorial is nothing but k plus 1 factorial. Now how we got this particular term k plus 1 is equal to this. I have taken 2. So you can take this term equal to k plus 1 only if 2 is less than k plus 1, where for k is actually the value of k you know already is greater than or equal to 1. So you compare here, 2 is can be 1 plus 1, and if you put any values, so this if you put 2, if you put 3, so when it k value is 1 plus 1, always this is less than k plus 1. So I just replace. So this is always less than k plus 1. So that's what I got it over here. So this is always less than k plus 1. So 2 is less than k plus 1. So I replaced with k plus 1, and that k can be anything greater than or equal to 1. So 2 is replaced with k plus 1. K plus 1 into next factorial is k, and I got k. So here you have 2 to the power k. So just check what you wanted. 2 to the power k is greater than or equal to k plus 1 factorial. So because I have assumed that because 2 is less than, here you need to write because, how I replace 2 with k plus 1 is nothing but because 2 is less than k plus 1 for k greater than or equal to 1. So this is an important step. You need to replace, how you replace 2, because 2 is less than k plus 1, k value can be replaced with anything greater than or equal to 1. Then we got this finally, this particular step. So this is statement is true for, so this precise S of n is true for k plus 1. Thus on the assumption that it is true for, S of n is true for n greater than or equal to 1. Hence by mathematical induction it has been proved that the S of n is true for n greater than or equal to 1. I'll repeat this step if you want. So here firstly we proved for 1 factorial, you know it is 1 itself. 2 to the power 1 minus 1 is 2 to the power 0. So that is equal to or greater than 1. That's what I got. Next I had k factorial. This is I assume to be true. This is the main step I assume to be true. Next from this I actually wanted to prove k plus 1 whole factorial 2 to the power k. So k plus 1 factorial I am supposed to get, and here 2 to the power k I am supposed to get. So I played the game over here itself. 2k minus 1 I wrote it as 2k divided by 2 to the power 1. That 2 I took it over here. So I got the left hand side over here as 2k, and here k factorial is already there. I need to get k plus 1. So I replace 2 with k plus 1, putting a condition that 2 is less than k plus 1 for k greater than or equal to 1. So this condition is very important. So this is how I put this particular condition and I played the game, and I got k plus 1 whole factorial. So this is our assumption. Thank you.